حياكم الله جميعا. I hope that you had an enjoyable vacation. حياكم الله. I hope that you had an enjoyable vacation, although, I was going to say that it's very difficult to have an enjoyable vacation if you get the results of an exam in the middle of the vacation. So I hope that, I know that some of you did well, some of you didn't do that well. So for those who didn't do that well, I think you just need to work a little bit hard in the next 7 or 8 days or so. I think that the course is not easy, but it's also not very difficult. I mean, most of the work in the course is, in my opinion, especially the last material, is kind of mechanic, meaning all you have to do is just understand how do you find the Fourier transform, how do you find the inverse Fourier transform, how do you find the Laplace transform, how do you find, and so on. So some of the topics are more mechanical rather than conceptual. Okay? Fourier series, for example, was something that is straightforward, in my opinion. It just needed a little bit of practice. The convolution also. There are some concepts in the course that are sometimes a little bit difficult to understand, but most of the course, in my opinion, is not that difficult to understand. Anyway, so for those who didn't do well in the midterm exam, I would encourage you to go and work a little bit harder. I'm always available, although I'm busy, but I will dedicate as much time as I need or as you need to help you. For example, if any concept is not clear, even if you want a problem session, I remember that I wanted to do a problem session, I think, before the midterm exam, but I think I got busy, or I remember. Yeah. If you want, problem session before the final exam, or even 2, I don't mind. Inshallah. Hopefully those 2 weeks, hopefully I'll be a little bit freer, and I can maybe do 1 or 2 problem sessions for you if you want. Okay, so let's set the midterm exam aside. What I did, gentlemen, yesterday and today is, I didn't send you anything about it, but I have already uploaded the updated lecture notes. I did it before the previous class, so about 2 hours ago. And what I did is also, as I promised you before the vacation, I recorded 2 makeup classes. You'll find them, I think they're lecture 30, I'm sorry, 29 and 30, I think, if I'm not mistaken. And they focus on Laplace transform. Because those 2 lectures were, let's say, given to you as makeup, any material that I give you in the final exam on this material will be significantly simpler than what I would typically give. If, for example, I explain those topics to you in regular lectures, I would probably give you a difficulty of this much. Because the lectures were explained to you in the form of makeup classes, I will significantly, whatever material I give you will be straightforward, will be simple, okay? I'm not sure that all of you will watch those lecture notes, okay? I would love to say, or would love to think that all of you will go and watch those lecture notes. So to kind of encourage you to watch those lecture notes, what I will do is, I promise you in the quiz and the course that I'll give you 6 quizzes. We have already taken 4. I'll give you the 5th one maybe next week or so, or either late this week or next week. Okay? The 6th one will be an open book, or let's say take home, not even open book. It will be a take home quiz. I'll give you the quiz, and I'll give you maybe 3 or 4 days to submit it. It will be more like a homework rather than a quiz, but I'll count it as a quiz. Okay? And the topic will be on the Laplace transform. So what I want you to do, gentlemen, is watch the last lecture before the vacation, which was lecture, I think, 28, and the 2 lectures that I added, which are, I think, 29 and 30. Yeah, because this is lecture 31. So watch those 3 lectures. Okay? And so they'll require you about 3 hours. If you haven't attended the last lecture, you'll have a total of 3 hours. If you attended the last lecture before the vacation, you need about 2 hours. And I took maybe 5 or 10 minutes addition on each one of those lectures. So roughly speaking, they're 2 hours and maybe 15 minutes or so. Okay? Watch those lectures and solve the homework assignment, or let's say the quiz number 6. And I'll give you 2 or 3 days to submit it. Okay? طيب يا اخوان تفضل عبد الرحمن, you have a question?
Yes, is the final going to be comprehensive?
Until now, I haven't decided on it, but most likely it will be maybe kind of comprehensive and not comprehensive. What do I mean by this? The material that is from, let's say, that was included in the midterm, most likely I'll not focus on it. Yani, okay, I'll tell you something. The Fourier series, I'll not ask you anything about it. Okay? Yani, because I never liked Fourier series, to be honest with you. So I'll not ask you about the Fourier series. Maybe the material that comes before the Fourier series, maybe I'll ask you something a little bit, something here or something there, simple questions. But clearly, most of the focus, I think, will be on the material that is after the midterm exam. I don't want to tell you now something definitely that this is what I will do. Give me a couple of days, inshallah. I will make up my mind on whether the final will be comprehensive or not, and the nature of the final. Now, unfortunately, the final will most likely be fully multiple choice, or at least most of it will be multiple choice. And please accept my apologies. I know that you don't like them. Wallah, I don't like it also. And the proof that I don't like also to give you multiple choice is you have seen, for example, that in the midterm exam, at least most of the questions, not all, but most of the questions I ask you to show me detailed solution. The problem with detailed solution is that they take a lot of time to grade, and I have very limited time. Now, I know that some of you have dropped. I think there were 1 or 2 people who have dropped from your course lately. So I think your number now is 32, I think, or 33. And the other course has, I think, 24 or 25. So if you add, still I have about 60 students. I'm not going to be able to grade 60 sheets with 4 or 5 problems, and it's the final exam, which means that the number of problems is probably going to be even a little bit larger, maybe 6 or 7 problems. I'm not going to be able to grade 60 sheets with 5 or 6 problems for each in about 2 days. You understand this? So I'm forced, honestly, I don't like it, but I'm forced. Wallahi, if the registrar comes today and say, you can submit the grades 1 week later, I will tell you, khalas, I'll give you the exam. I'll probably maybe make 1 problem or 2 problems. And maybe 20% of the problem of the exam will be multiple choice, but the rest will be solving. But unfortunately, the registrar will not do this. Okay, so I'm forced to give you most of the exam. I'll try as much as possible to give you at least 1 problem that's solving. If I can't, for whatever reason, then most of the exam or all of the exam will be multiple choice or true or false or something like this. Okay, so my apologies for this. Believe me, well, I don't like it, but it's out of my control. So anyway, just give me a couple of days. I'll make up my mind regarding the format of the final exam and whether it's going to be comprehensive or not. Okay, Juan? Right. So as I mentioned also, I'll probably give you a quiz number 5, either this Thursday or Sunday of next week. Quiz number 6 is going to be that take-home quiz. So this basically will make it 6 quizzes for you. And after that, I will take the highest 5 and I'll drop the lowest one for all of you. Okay? Okay, so let's go to the lecture now. So as I mentioned, gentlemen, just a minute ago, the Laplace transform material is covered in lecture 28 and makeup lecture, which is lecture number 29 and 30. Those 3 lectures cover everything that I want you to understand in the Laplace transform. Okay? There are a lot of cases in the Laplace transform that I will not ask you because they're kind of complicated. And whatever I ask you in the Laplace transform in the final exam will be, relatively speaking, simple. I promise you this. Okay? Okay. So now we'll go to the next topic, which is if you think about it, since the beginning of the semester, since the beginning of the summer, until last class, which includes even the makeup class, what we have been talking about is continuous time signals. What do we mean by continuous time signals? Those are signals that are defined for all time, from -infinity, let's say, to infinity. Or even if they're not defined for all time, they are defined, for example, for time between, something like this. The signals that we have been talking about since the beginning of the course are always signals that look like this. Or if they're not signals that look like this, maybe we're only interested in the signal over a specific range of time. For example, from 2 to 10. Okay? But in every point, every time between 2 and 10, I can tell you what is the value of that function, or what is the value of that signal, and you can tell me that x of, for example, 3 is equal to 4, x of 5 is equal to 2, x of 3.6289 is equal to 7, x of pi, where pi is an irrational number, is equal, for example, to 8, and so on. So basically, all of the signals that we have been talking about so far are what we call continuous time signals, signals that are defined for all time, typically for all time, from minus infinity to infinity, like the sine, or cosine, or exponent, or all of those functions, or the step function. Even the impulse function, by the way, even the impulse function is defined for all time. It happens that at t equal to 0, it's equal to infinity, and at other times, it's equal to 0, but it's defined for all time. Now, starting from this class, we'll start to talk about a class of signals which is called discrete time signals. What's the difference between continuous time signals and discrete time signals? Continuous time signals are defined for all time. Discrete time signals are defined only for specific time instance. For example, a discrete time signal, okay, may be defined, for example, for t equal to 0, and for t equal to 1, and for t equal to 2, and for t equal to 3, and so on, and maybe negative times, minus 1, minus 2, minus 3, and so on, okay? But for discrete time signals, gentlemen, if I ask you, for example, what is x of 0, you tell me that it's equal to 3. In here, it's equal to 3. Okay? But what is x of 2.3? It's not equal to 0. Discrete time signals, gentlemen, are not, between those values at 0 and at 1 and at 2 and at 3. Okay? Between them, the signal is not defined. So it's not defined. So we don't say that the value of the signal is equal to 0, but we say that the signal is not defined. Okay? So those signals, discrete time signals, are only defined at specific time instance. In fact, each one of those, we call it a sample. So basically, this is the sample of 0, the sample at 0, this is a sample at 0. This, the value there is the sample at 1, this is sample at 2, this is sample at 3, and so on. Okay? So the signal is not, we don't have an infinite number of values for the signal. We may have an infinite number of values, but the infinite number of values don't come after each other. We don't have a value for the signal at 0 and at 0.000001 and at 0.00002 and so on. We only have them, for example, at integer values of t, or at 0 and 2 and 4 and 8 and 10 and so on, or at 0 and 0.5 and 1 and 1.5 and 2 and 2.5 and so on. Yeah, the important thing is that the signal is only defined at specific time instance, but it's not defined for continuous range of time. Okay, gentlemen? This is the difference between continuous time signals and discrete time signals. Now, our discussion today is kind of a mix between the two. What do I mean by mix between the two? The signal, by the way, my computer today, even in the previous class, has continuously been jumping. I don't know why. Sometimes, even without touching it, I find that it jumps 30 pages earlier or 20 pages later or so. So it jumped maybe 50, 60 earlier. Just give me a minute. Let me use this. I'm trying to use that scroll bar on the right, but it's not working. So now we're talking about, at least the discussion that we're going to be discussing today, or what we're saying today, gentlemen, is kind of a hybrid between the two. What do I mean by hybrid between the two? Those are signals that we're starting with as continuous time signals, signals that are defined for all time, but we are interested only in maintaining specific times of that signal and setting the rest to be equal to 0. Meaning the following. I just mentioned that this signal, the upper signal here, is defined for all time. The lower signal is only defined for specific time instance, or basically only for the lower signal, I'm only defining the signal at the locations of those samples. Okay? Now we can define a signal in which it looks like it's a continuous time signal in which I can plug in any value of t and get a value for that signal, okay? Where at the locations of the samples, the value of the signal is equal to 3 or 2 or 5. And at the locations other than the locations of the samples, and in between, in the ranges in here that I'm coloring in here in the orange, the value of the signal is equal to 0. This is what we call continuous time signals, okay, that are sampled, or let's say sampled continuous time signals. This discussion is only today. Starting from next class, okay. Just give me a minute. Okay. Can you just give me a minute, because I think there's a team or some technicians who are installing something. Let me just talk to them. Ask them to. Do you need to do it now? خلاص you're done. Okay. Thank you. They're installing those, I don't know, security cameras in the whole building, so they are drilling in the ceiling. Okay, the gentleman said that they're done. Okay, so gentlemen, what I'm saying is that the signals that we're talking about today are signals that are still defined for all time, except the difference is that at the location of the samples, at, for example, integer values of time, okay, the signal has a specific value, which could be 3, 5, -2, and whatever. And in between those samples, the value of the signal is equal to 0. The signals, the discrete time signals, gentlemen, that I talked about a minute ago, those are not defined between the samples. The signals that we're talking about today are defined between the samples, and it happens that the value of the signal at those times is equal to 0. Okay? Right. Now, one of the things that we always have to understand whenever we are talking about continuous time signals and discrete time signals is, how do you convert a continuous time signal to a discrete time signal? And how do you convert a discrete time signal to a continuous time signal? Is the conversion easy? Can you always do it? And so on? Yes, sometimes you can do the conversion, sometimes you cannot do the conversion for reasons that we'll talk about, inshallah, later today. Okay? But there are devices that will allow you to take a continuous time signal and convert it to discrete time signal. And there's also a device that will allow you to take a discrete time signal and convert it to a continuous time signal. Now, the device that allows you to take a continuous time signal and convert it to discrete time signal, okay, is usually called an ADC. Okay, ADC stands for analog to digital converter. Okay. You'll find this device in thousands of, let's say, applications. Whenever, for example, your mobile phone. Is your mobile phone a digital device or is it an analog device? What I mean by, maybe I didn't explain to you. Digital device means it works on numbers. Analog devices work on signals, on continuous time signals. Do you think that your mobile phone is a digital device? By the way, I do not have my mobile phone on, so I don't know. If you're raising your hand or just speak. I do not know who's raising.
Digital.
Digital, absolutely. Yes, certainly. Your mobile phone is a digital device. Yes, you're right. Okay. What about modern TVs? Most modern TVs nowadays, are they analog or digital devices?
Also digital.
Also digital.
Also, yes. Analog, let's say all TVs of maybe up to, I'll say 20 years ago, maybe, probably 20, 25 years ago, were analog. All of the signals that they worked on were analog signals. Nowadays, all TVs, I can guarantee to you now that, in fact, if you have an analog TV, you probably can put it in a museum now. Right? Honestly, by the way, I'll just mention this because I think that it's funny. Sometimes when I go to kind of places that collect old stuff and put them, I feel sorry. Why? Because I know that you, as the new generation, when you see things like that, you say, wow, they used to live, let's say they used to use devices like that. Okay? For me, this is how I lived. By the way, I'm 50 now. Okay. In fact, we're in August. In September, I'll become 50. Okay. Yani, I lived. Let's say I lived with the old technology, and I'm living now with the new technology. Okay. When I see something like this, I feel that the new generation probably think that those who lived with the old TVs, خلاص, this is the old generation that needs to, let's say, die and just disappear. Okay, so it always gives me mixed emotions whenever I see those devices. Anyway, so I was saying that 25 years ago or so, TVs were analog. Nowadays, all TVs are digital. Your mobile phone is digital. Your computer is digital. Almost all devices now that you have, by the way, at your house, even, by the way, now refrigerators are becoming digital devices. You know that probably now, in a few years, when you buy a refrigerator, your refrigerator will be able to connect to the internet, yeah? And it will tell you, you can just connect to it, and it will tell you that you are, for example, you need to buy some juice, or you need to buy some milk, or, for example, you only have 2 kilograms of meat in the freezer, and so on. Okay, so everything now is switching to digital. However, the real life is typically analog. For example, if I ask you how heavy you are, or let's say if you measure how heavy you are and plot it versus time, you expect that your weight is going to look like an analog signal. Okay? It increases and decreases, okay, continuously. Yeah, I can find your weight now. I can find it after 1 second. I can find it after 2 seconds. I can find it after a fraction of a second. Okay? So the weight of human being is analog. The age of human being is analog. Yeah, a lot of phenomena in real life are analog signals. However, whenever you want to operate, or you want, for example, to process or manipulate analog signals on a digital computer, or using your mobile or so, clearly your mobile phone does not understand analog signals. So how does your mobile phone convert the analog signals to digital? It uses one of those devices, ADCs. Okay? So an ADC, what does it do? It takes an analog signal and converts it into a digital signal. Okay? Now, the conversion between analog and digital is a two-step process. One of the steps is called sampling, and the other step is called quantization. Quantization or quantizing. Okay? I will not talk about quantization now. I'm only interested in sampling. But understand that for you, or for your mobile phone, to convert your speech, in fact, even your speech is an analog signal. Your speech is vibrations in the air. It's let's say, air pressure. It's pressure in the air. And this is an analog signal. If you plot the pressure of air, because while you speak, okay, it's basically an analog signal. Now, the voice that you're hearing is coming from my mouth, okay, which is an analog signal. So basically, the microphone that I have is connected. I guarantee to you that it's connected to an analog to digital converter to take that signal and convert it. The first step, as I mentioned, it will sample it. And then the next step is that it will quantize it. I will not talk about quantization, as I mentioned. I will only focus on sampling. So the first step of any conversion from continuous time signals to discrete time signals is sampling. Okay, gentlemen? Right. I will show you some math, by the way, a little bit of math, but you do not need to worry about the math a lot. Right? I will not ask you about the math that comes later. But I could have, because I will reach a conclusion, inshallah, in probably 10 or 20 minutes. Right? I could have just given you this conclusion and said, live with it. But I think that if I don't show you the steps of reaching this conclusion, you'll not understand it, and it will not sink into your brain. Okay? So now what I will discuss is what happens if you take a signal and sample it. Okay? How, yeah, basically what I'm going to do is I'm going to discuss, or I'm going to talk about the details of sampling. Okay? Now, what is the process of sampling? Sampling is basically taking a continuous time signal like this one. Let me just erase everything here and sketch it. Sketch a fresh form of it. Okay. What is sampling, gentlemen? Sampling is a very simple process where it says the following. You take a continuous time signal like this, and you're interested only in capturing specific points of that signal. Meaning, for example, assume that this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, -1, -2, -3, and so on. This signal, the signal that I've sketched, is a continuous time signal. It's defined for all time, from -infinity to infinity. Whenever you want to convert it into digital domain or convert it basically into discrete time signal, you have to select what we call a sampling period, TS. What is a sampling period? You'll decide, for example, that every 1 second, I'll pick a value from that signal. Okay? Every 1 second, I'll pick only the value of that signal. And then between 1 and 2, I'll not pick anything from that signal. At 2, I'll pick another sample of the signal. Between 2 and 3, I'll not pick anything. At 3, I'll pick a third sample, and so on. So what is the concept of sampling? Sampling says basically that you go to that signal and select only values of that signal that exist at the locations in which you want to take the samples. Now, there is something that we used or that we learned earlier in the course that allows us to take a sample. Anybody remembers what that thing is? What was the thing that will allow us to, if we wanted to sample a signal at a specific time, we can multiply that signal by this thing, okay, which will provide us with, I do not see who's raising their hand, so you can just speak up.
Delta function?
Delta function, absolutely right. Yes, you're right. Okay, the impulse function, gentlemen, is a function that allows us to sample a signal. I think one of you also had maybe a different answer, or anybody is raising their hand?
That's right.
Okay, no problem. Okay, sorry, I came a little bit. I was busy just before the class, so I didn't have the time to set up my mobile phone to see who's raising their hands. My apologies for this. Okay, so basically, if we multiply a signal by an impulse, okay, what does that impulse do? Remember, we said that if we have x of t multiplied by delta of t minus t0, okay, this is, by the way, if you remember, this is called the shifting property. Whenever you multiply any signal by an impulse, you can simplify this, yeah, or this basically becomes equal to x of t0 multiplied by the impulse. You do not get rid of the impulse. The impulse is still there. You can get rid of the impulse only if you were integrating, but we're not integrating here. Okay? So this becomes equal to delta of t minus t0 multiplied by x of t0. Okay? Basically, what does this say? It says that if I have this signal in here, let me just sketch it again. If I have any signal like this, and I multiply it by an impulse that looks like this. Okay? Basically, what the impulse will do is it will set the product of those two. If I take the product of those two, okay, I'll get 0 everywhere. Let me just make it thicker. Okay. I'll get 0 everywhere. Okay, with the exception of the location of the delta, where I will get the delta, but the delta will have a magnitude. And instead of this delta having a magnitude that is equal to 1, now the impulse here, or the delta, will have a magnitude that is equal to, if this is x of t, it will have a magnitude that is equal to x of t0, where this is t0. Okay? So now I ended up, by multiplying the impulse by that signal x of t, I ended up with an impulse that has a magnitude or an area under it that is equal to x of t0. So now we can use the same concept to sample a signal multiple times, not only one time. Clearly, this impulse is only sampling the signal at only a single time, at t0. What if I put infinite of those, every 1 second, for example, or every 2 seconds, or every whatever sampling period that I'm interested in, every ts, meaning put one at 0, put one at ts, put another one at 2 ts. Sorry, my handwriting now is a little bit large. This is at ts, this is at 2 ts, at 3 ts, and so on, until a million ts. Okay? And the same thing on the negative side. Okay? If I put impulses at every one of those after every ts seconds, then I am sampling the signal x of t every ts seconds. Where ts could be, by the way, 1 second, it could be 10 seconds, it could be 1/1,000,000 of a second. Right? So basically, this process is doing the sampling for us. Okay, Juan? And in fact, this is what I'm saying in here. We know that this is true. I'm calling, by the way, this. I'm calling this. I'm calling it xs of t. So think of this as one sample, x sample of t. Okay, I'm obtaining one sample of t at t0. Now I can always represent, or I can always define a function, periodic function, which I'm going to call it delta ts of t, to be equal to an infinite number of impulses, and those impulses come at constant intervals, and the constant intervals there is ts. Meaning, if you plot this, if I ask you to plot this, you'll tell me that this is what we call, they usually call it a train of impulses. One impulse at 0, one impulse at ts, one impulse at 2ts, and so on. All of the impulses have magnitude that is equal to 1. But the impulses are located ts seconds apart, from -infinity to infinity. I'm calling this signal delta ts. So delta ts is not a single impulse. It's a periodic sequence of impulses that come every ts seconds. And if I combine all of those, if I add all of those, or if I put them into a summation, then I get what we call a train of impulses. Okay, and I think I have a figure of it in here. Okay, no, I don't have the train of impulses. I just have the. Okay, now once you multiply x of t by that train of impulses, let me write it this way here. Okay, I can now define another function which I'm going to call x bar in here. And honestly, I don't know why I called it x bar, to be honest. Okay, maybe I'll change it in the. I already uploaded, by the way, this material, but maybe I'll change it for you later. Okay, let's define x bar to be equal to x of t multiplied by this. So I'm just taking this and multiplying it by x of t. Okay, now because x of, look, the summation here is in terms of n. Yeah? There's a t in there, but the summation is in terms of n. And this function, x of t, is a function of t. So I can take x of t inside the summation, or I can take it out. It's just like if I have an integration with respect to dy, and I have x in here, I can take the x inside, or I can take it out, because x is a variable, and I'm integrating with respect to y. Okay? I'm doing something very similar in here, except that I have a summation in here rather than an integration. So the summation in here is in terms of n, where n is there. I clearly cannot take the impulse outside, because the impulse is a function of n. But I can take x of t, I can take it inside. So I just brought x of t in there. Now, whenever I have x of t there multiplied by an impulse, we know using that property, the symplectic property, I can now take this thing and substitute it in there. Now, this basically tells us that x bar now is a sequence of impulses that happen every ts seconds, and each one of those impulses is weighted, or basically is scaled, by a value that is equal to the value of the function x of t at that location, at the location of the impulse. Okay? And this is basically what I'll get. If I have this thing and I sample it using a train of impulses, I end up with x bar, which is equal to, this is just for indication. This dashed line is just for indication. It's not there. Okay? And theoretically, I should say that this is basically this is x bar. I'm removing this dashed line is just x of t, and I just wanted to show you that, look, x of t or x bar, the impulses, the magnitude of the impulses just follows x bar, or I'm sorry, follows x. Okay, so x bar does not have this dashed line. It's just a sequence of impulses, but different impulses have different magnitudes or different areas or different, let's say, weights that are functions of x of t, of this signal, here. Okay, gentlemen? Okay. So far, so good. Now, this is basically what your mobile phone, think of it this way, is doing to your voice. It's sampling your voice at constant intervals. And by the way, for human voice, usually they sample it at, roughly speaking, 8,000 samples per second. Roughly speaking, the duration between each sample and the next sample is 1/8,000 of a second. 1/8,000 of a second is, roughly speaking, 0.000, I think, 125 seconds. Now you may say, why are they sampling it? This is basically the period of this what we call the sampling period, which means that the sampling frequency, okay, is equal to 8,000 samples. 8,000 samples per second. Now you may ask, why is my mobile phone sampling my voice at a sampling rate that's equal to 8,000 samples per second? It looks like a large number. In fact, it's not. Okay, but there's a reason why it is. Your mobile phone is sampling at this value. If it samples at less than this value, something is going to happen, which will result in the person who's listening to your voice on the other end of the mobile phone call, okay, he's going to hear your voice distorted. Okay? Trust me on this. If your mobile phone samples at less than 8,000, maybe if it's sampled at 7,500, it's okay. But if it's sampled only at a sampling rate of 2,000 samples per second, then at the other end, the person who's trying to listen to you, he's going to hear your voice with very low quality. Why is this? This is what I'm going to try to explain to you in the next few minutes. Okay? Now, let's say that x of t, my x of t, the signal x of t in there, gentlemen, this x of t has a spectrum, and if I take the Fourier transform of this, it has a spectrum that looks like this. Okay? Now, I remember I talked about the concept of bandwidth when I talked about filters, but I didn't talk about the concept of bandwidth when I talk about signals. Any signal, gentlemen, any signal in the world has a bandwidth. What is the bandwidth? The bandwidth is how much frequency, okay? What is the frequency range of that signal? Meaning how much frequency from 0 all the way to the highest frequency of that signal. Okay? Meaning human voice, in fact, has a bandwidth that is approximately equal to 3,500 hertz. If you take, let's say, if you record 10 seconds of your voice or so and find its Fourier transform, you'll find that the spectrum of your voice is going to extend, roughly speaking, between 0 and 3,500. A woman's voice extends a little bit more, maybe up to 4,000 hertz. Okay? If you bring some of those people who have very, I don't know what they call it, sort of khashan, or something like this, okay? Their voice typically goes maybe from 0 to 2,500 maybe. Okay? So different human beings have, let's say, a voice that have, or let's say, have voices that have different bandwidths. But typically, a human being, we can say that the bandwidth of a human being voice is, roughly speaking, up to 3,500 hertz. Okay? Now, when you sketch the spectrum of the human voice, this is how it looks like. Okay? So I just sketched the spectrum of a signal, okay, which looks like a triangle. And B there is basically the bandwidth. B is defined as the bandwidth of that signal. It's the maximum frequency content of that signal. And I think I remember, if I'm not mistaken, I showed you in that application that I had in my mobile phone when I recorded human voice, when I recorded my voice and showed you what happens when I clapped. If you remember, the clap had much higher bandwidth. The clap, in fact, the tasfiq, okay, it has much higher bandwidth. Why? Because the clap was like an impulse, and we said that an impulse has a bandwidth that is theoretically equal to infinity. But the human voice, as I mentioned, has much lower bandwidth than the clap. Okay, it's only about 3,500 hertz or so. Okay. Now, what happens if I have x of t? Where is it? If I know the spectrum of x of t, where is x of t? If I know that x of t, just give me a minute. Let me just clear in here. Oops. If I know that x of t, let me just make this up. If I know that x of t has Fourier transform, which is capital X of omega, yeah? And capital X of omega looks like this. This is minus b. By the way, the bandwidth of this signal is not equal to 2b. Some people sometimes make a mistake and say that the bandwidth is all of this interval. No. The bandwidth is always measured on one side, meaning from 0 to b. Okay? So the bandwidth of that signal is equal to b. It's not equal to 2b. Okay? So let's say that this is capital X of omega. Now the question is, if I take this x bar of t, which is equal to, we defined it, or we found it to be equal to sum from n equal minus infinity to infinity of x of n ts. In fact, let me not even use this. I'll use this form. I think because it's easier. Okay, x of t times delta of t minus n ts. Okay? Assume that I want to find, or basically this is what I'm trying to do. If I know that let me just move this up a bit here. If I know that x of t has a spectrum which is capital X of omega, what is the spectrum of x bar of omega? Okay, where x bar, if you think about it, is equal to x of t multiplied by train of impulses. Okay? Or I can even take x of t outside if I want. Okay, x bar of t is simply equal to x of t multiplied by the train of impulses. How will the spectrum of this thing look like? This is basically what I'm trying to do now. Okay? And to be able to do this, let me say the following. We are sampling at a sampling period which is equal to Ts, okay? Which means that we can define something called the sampling frequency, omega s, which is equal to 2 pi over Ts. I can define either the sampling frequency in hertz, which is equal to 1 over Ts, or I can define the sampling frequency in terms of radians per second, which is going to be equal to 2 pi divided by Ts. So this is just a constant. And if I'm sampling at, if the sampling period is equal to 1 over 8,000, the sampling frequency becomes equal to 2 pi multiplied by 8,000. This is just a number. What I'm trying to say is that this is just a number that depends on the sampling period. Okay? Now, this train of impulses, which is defined as this, I can always write it, and it may not appear to you directly, but you can always write this. You see, this is a periodic signal, isn't it? This thing is a periodic signal. It's a train of impulses. Yeah? So it looks like this. Right? A train of impulses that goes from minus infinity to infinity. Right? You can always write it using the Fourier series expansion, and if you do this, you see that this basically becomes the Fourier series expansion of that signal. And there is a reason why I'm doing this, because it will make our life significantly easier. We know that the train of impulses, gentlemen, if we try to represent it in terms of its Fourier series expansion, we can write it as this. Believe me on this, okay? Take it as a fact, okay? In fact, this material, I got it from an old lecture note for EE370. And I had the material for finding the Fourier series coefficients from this signal. And I applied the Fourier series coefficients on this signal, okay? And I got it. I just removed that material because I felt that it was not of importance, okay? But if you try to find the Fourier series expansion for this train of impulses, this is how it will look like. Now, what does this contain? It contains a DC value. Let me just show you what that, when you try to represent that train of impulses using this, using the Fourier series expansion, and I'm using in here the trigonometric Fourier series expansion, the format of the Fourier series that has the cosine. Okay? You have a DC component which is equal to 1 over T0, 1 over Ts, I'm sorry, and you have then 2 over Ts multiplied by cosine omega st plus 2 over ts multiplied by cosine 2 omega st plus 2 over ts multiplied by cosine 3 omega st, and so on. And this continues until infinity. Okay? So I have, in fact, the Fourier series expansion there requires infinite number of components. I'm almost done. Now, if x bar is equal to this, I can remove this thing and replace it with its Fourier series expansion. Put like this in place of that. Okay? And in this situation, I'll get 1 over ts multiplied by x of t. Basically, I remove this. I remove this and took all of this thing in there and plugged it in its place. Okay? So I'll get x of t multiplied by 1 over ts plus x of t multiplied by this plus x of t multiplied by this, and so on. Each one of the cosines will be multiplied by x of t, and also the constant value, the DC value, will be multiplied by x of t. Okay, and this is basically the formula that I'm going to get for x bar, which represents the sampled version of x of t. I'm almost done. Now we know if I have, let me see if I can. Where's that thing that I wrote? Okay. Let me just copy this in there or move it. Down. I put it here. Okay. Now, if I know the following, okay. If I know the Fourier transform of this, okay, the Fourier transform of this was capital X of S, capital X of omega. I'm sorry, capital X of omega, which had this shape. This is capital X of omega. Okay, what is the Fourier transform of this, which contains infinite number of components? Each component, the first component is simply x of t multiplied by a constant. The second component is x of t multiplied by a constant, but multiplied by a cosine omega st. The third component is x of t multiplied by the same constant, multiplied by cosine 2 omega st, and so on. You remember when we multiplied a signal by a cosine in time domain, how did its frequency domain look like? Its frequency, or let's say Fourier transform. How did it look like? Anybody remembers? If you have x of t, if this is x of t, I'm sorry. Let's say x. Sorry, my apologies for this. Okay, if this is x of t, and it has Fourier transform that looks like this. Okay, what is the Fourier transform of x of t multiplied by cosine, let's say omega t, some omega 0 t?
Like discrete time function.
Discrete. What do you mean by discrete time function?
The shape of the function when the delta function will up and
No, not exactly. No, this is not what will happen. Okay. In fact, I can go to the Fourier transform table above. You see that whenever you multiply a signal by cosine in frequency domain, this is what you do to it. You scale it by a factor of one half. You scale this thing by a factor of 1/2, and if this thing, for example, is equal to a, you get 2 copies of it, one at minus omega 0 and one at omega 0. Okay, and it is scaled by a factor of 1/2. In fact, this is the Fourier transform. Let's say, or sorry, this one is the Fourier transform of x of t. If I multiply x of t by a cosine, the Fourier transform of it becomes equal to a copy of the Fourier transform of the original signal, but 2 copies, one shifted to the right by omega 0, or by whatever frequency I'm using here, and one shifted to the left by the same frequency. And it is scaled by a factor of 2, which tells us that the Fourier transform of this okay, of this thing in here, okay, becomes the following. It becomes equal to the Fourier transform of the original signal, scaled by a factor of 1/ts. Okay? Added to it the Fourier transform of x, shifted to the right by omega s and to the left by omega s, and scaled by a factor of 2 over ts. And there's also a scaling factor of 1 over 2 because I'm shifting to the right and shifting to the left. Plus the Fourier transform of x of t, shifted to the right by double that sampling frequency to the right and double the sampling frequency to the left, and scaled by 2 over ts and scaled by 1 over 2. And so on. And I keep doing this for all of those components until infinity. In fact, I can write it this way. X bar of omega is equal to x of omega scaled by 1 over ts, and 1 over ts multiplied by copy of this thing, shifted to the right and shifted to the left. Okay? And notice that in here we started with a 2 in there. There's a 2 in here. But in here I have a 1. Why do I have a 1? Because when you multiply by cosine, the formula, or let's say the Fourier transform property, when you multiply by cosine, it says that you have a scaling factor of 1 over 2. So the 2 there disappeared, and I get a 1. Okay? And also, I get this thing shifted to the right and to the left by 2 omega s, and shifted to the right and to the left by 3 omega s, and so on. Okay? In fact, you can write it eventually as an infinite sum, which has a constant which is equal to 1 over ts outside, and then an infinite sum of copies of the Fourier transform of the original signal. Yeah, meaning this thing think of it this way. The Fourier transform of this, okay, in here, let me write it, becomes equal to this, and this, and this, and this, and this, and so on both sides. This is basically the Fourier transform of a signal when you sample it. Okay? The spectrum of the original signal before sampling, you just copy it, make infinite number of copies to the right and infinite number of copies to the left of that signal. Okay? And this is basically the conclusion that I was trying to reach. This is basically the shape of it. Maybe in a kind of in an accurate form. Okay. As you notice, in here I'm scaling it by a factor 1 over ts because of this. Because the original signal, if you notice in here, I had a height of it that is equal to a. Okay? In here I have a height that is equal to a divided by ts. Okay? And then I have infinite number of copies. Each copy happens at omega s, 2 omega s, 3 omega s, and so on. And minus omega s, minus 2 omega s, minus 3 omega s, and so on. Okay? Now comes the important conclusion that all of this discussion was trying to reach. What happens if we sample a signal at a very high rate? For example, if I have my voice, we said that our human voice has a frequency of, let's say, 3,500 hertz. Okay? Or in radians, it's 2 pi times this, radians per second. Okay? What happens if I sample this at 1,000,000 samples per second? Where does this copy come? It happens at 2 pi times million. Let's say 10 to the power of 6. And this comes at 2 pi times 2 times 10 to the power of 6. Okay, sorry, let me just organize my writing. Okay. If you sample at a very high sampling rate, yeah, this becomes at 0. This becomes at 2 pi times 10 to the power of 6, for example. This becomes at 4 pi times 10 to the power of 6. This becomes at 6 pi times 10 to the power of 6, and so on. Okay? Now, 10 to the power of 6, while this thing is only 3,500, and this point becomes at, you see, this region here is 3,500. And this region here has a width that is equal to 3,500. Okay? So clearly, this point here is less than 2 pi times 10 to the power of 6 by 3,500. Okay? So this becomes at 2 pi times 10 to the power of 6 minus 3,500. Okay? So clearly, those copies, this copy and this copy, are very far away from each other, right? Those copies become very far away from each other. In fact, the difference between them is, roughly speaking, 1 million hertz. The difference between this, the duration or the difference between this, if someone asks you in this situation, how far are those two from each other? Are they touching each other? No, they're not touching each other. Because one copy goes from 0 to 3,500, multiplied by 2 pi. Okay? And the other copy goes from the sampling frequency omega s, less than the sampling frequency by 2 pi times 3,500, and greater than the sampling frequency by 2 pi times 3,500. Yeah, it's something like that. Let me just use maybe simpler numbers. In here, 10, and this is minus 10. Sorry, this one's 10. I'm just using in here smaller numbers, 10 and minus 10. And let's say that I put the other copy in there because the sampling frequency is very large. I put the other copy there at 1,000. Okay? So clearly, the copy that I have in there will come in here. So this will become equal to 990, and this becomes at 1,010. Okay? So clearly, the difference between those is something like 980. So the two copies are very far away from each other. Not only those two copies are far away from each other, also those two copies are far away from each other. Those two copies are far away from each other. Those copies are far away from each other, and so on. All copies of the original signal are placed very far away from each other. Okay? Now, if someone asks you, can you get this original signal from this one? Do you think we can get that signal that is above from this signal in here? What can we do? Is there a device that will allow us to from this one? Because the answer was there in the figure. I don't know if you saw it or not. Okay. Can we get, gentlemen, that figure, which is, sorry, can we get this signal in here, which only has one copy, okay, which exists around 0? Can we figured out how to get this, the lower one from the upper one. To get the lower one from the upper one, we have to sample the signal. When you sample the signal every omega s, we go from the upper one to the lower one. Now the question is, can we get from the lower one to the upper one? Is there a device that will allow us to go from the lower signal in here to the upper signal here, the one that I'm coloring now in yellow? Do you think that there is a device that will do this for us?
A filter. A filter.
A filter, absolutely right. Thank you so much. Okay, a filter. What type of filter?
A low pass.
Low pass filter. Perfect. You're absolutely right. Okay. In fact, if we put a filter like that, what does that filter do? It will only pass this copy. By the way, each one of those is called an image. It will only pass the image around 0 frequency. What will it do to all of those images? It will filter them out. When you filter all of those images out, you end up with the original signal. Okay? In fact, what we just did, okay, by sampling, we went from continuous time to discrete time, or think of it this way. And by sampling, we moved from continuous time to discrete time. By putting the signal in a filter, we moved back from discrete time to continuous time. Okay. Now you'll be able only to. Okay, let me just mention this, and I promise you that I'll repeat it next time. Okay. Do you think that regardless of what sampling frequency we use, you'll always be able to go from this to the upper one without any distortion? Again, let me say it this way. Okay? We figured out that if we have a signal in here and we sampled it, we'll go from the upper one to the lower one. Now we saw that if we put a low pass filter in here, we'll be able to extract this one and cancel all of those, which means that we'll go from the discrete time signal, from the sample signal, back to the original signal. The question that I'm asking you now is, do you think that there exists a condition that must be satisfied if we don't satisfy this condition, we will not be able to go from the lower signal to the upper signal. Or even if we go, the upper signal will be a distorted version of the lower signal, of the original signal. Meaning, I record my voice, sample it, and then I return it back to the original signal without the sampling, but you find that my voice is not as it was. It's not the same quality of the voice that I had before. Okay? I'll stop at this point. Next class will start from this point. Okay, Juan? Okay? So
نقدر يا دكتور نحط multiple filters ولا؟
طيب, I'll answer your question inshallah next class. I think I understand your point. Remind me next class of this point, and inshallah I'll answer it. Okay?
طيب دكتور, ما هو الامبليتود is different?
لا, the amplitude, okay, you're absolutely right. The amplitude is different, but I can always amplify or attenuate a signal. The amplitude is not really an issue. Whenever you have a signal that is attenuated, you can always multiply it by 10 and put it into an amplifier, for example. Okay? You see, the amplitude is not really the issue. The issue is in the frequency, let's see, in the horizontal dimension, not in the vertical dimension.
دكتور, البيريود هي الissues يعني؟
هي البيريود or the frequency, yes. Think about the following. I'll just mention this, and by the way, if you want to leave it, okay. What happens if I reduce the sampling frequency? What happens to those copies? If I reduce the sampling frequency, you see this is omega s in here, and this is omega s, this is 2 omega s, this is 3 omega s, and so on. What happens if you reduce omega s? What will happen to the different images? This will probably give you a hint. There will be a point where something will happen to the images that will not allow me to go back to the original signal exactly. I may be able to come up with part of the original signal, but not the original signal perfectly. And this is the thing that we need to discuss next class. Okay, Juan? Okay, I'll stop at this point. If you have any questions, please ask. If you don't have any questions, inshallah, I'll see you tomorrow.